This is the power required curve for the R-22, which would be very similar for any helicopter. Here at zero airspeed, a fairly high power is required if you were hovering on a ground effect. As you start to move forward, the power required drops off very rapidly as you go through effective translational lift, and then bottoms out here at about 53 knots. Then starts back up again and goes up quite steeply as you go into high-speed flight. This point at 53 knots, where the minimum power is required, actually determines three of the basic characteristics of our aircraft. It will determine our speed for maximum endurance, because obviously we're burning less fuel at that airspeed than at any other airspeed, and therefore can stay up in the air longer. It also will tend to determine our best rate of climb speed. Because we're using the least amount of power for level flight, we have the greatest amount of power left over to climb with. And it will tend to be at or very close to our speed for a minimum rate of descent in auto rotation. If I draw a vertical line through that point at 53 knots, I can arbitrarily define everything to the left of that line as the back side of the power curve, and everything to the right as the front side of the power curve. There's a great deal of difference between operating an aircraft on the front side of a power curve and operating the aircraft on the back side of the power curve. On the front side of the power curve, everything is quite normal, natural, and stable. It takes more power to go faster, less power to go slower. For instance, if I'm trimmed out at 80 knots, and it takes 77 horsepower to maintain 80 knots, if a gust or turbulence were to momentarily speed me up to 90 knots, there it would take 87 horsepower to maintain 90 knots, but I only have 77 horsepower pulled in. So the helicopter is going to slow back down. Conversely, if the turbulence were to momentarily slow me down to 70 knots, where it takes only 67 horsepower, but I've got 77 horsepower pulled in, since I have more power pulled in than I need for 70 knots, it's going to tend to speed back up. In other words, it's going to tend to come back to its original trim condition. Okay, back on the back side of the power curve, everything is quite different. It takes more power to go slower and less power to go faster. Frankly, you have a hard time thinking of anything that works that way. Certainly an automobile doesn't work that way, a boat doesn't work that way. You have a difficult time thinking of anything that requires more power to go slower and less power to go faster. Furthermore, it's unstable. If I'm trimmed out at 30 knots, for instance, and it's taking 67 horsepower to maintain 30 knots, again, if I allow that helicopter to momentarily speed up to 40 knots, where it takes only 63 horsepower, it's going to want to speed up even more. And the more it speeds up, the more it's going to want to speed up. Conversely, if I allow it to slow down a little bit, then it's going to require even more power, and the more it slows down, the more power it's going to require, and so on. So it's unstable with power and airspeed. And this frequently gets involved in training accidents and other accidents with the helicopter. The pilot, one of the things the pilot will do wrong is he will get on the back side of that power curve where it is unstable with power and airspeed. Very quickly he'll end up at a very, very low airspeed.